In the deep cosmos of Andromeda, a galaxy emerges like ripples in the cosmic sea, where the dance and light of stars converge. Andromeda cradles a sense of mystery. With a soft glow, countless stars illuminate the path of the galaxy. The brilliance of starlight surpasses the galaxy, captivating our eyes with its beauty. The embrace of Andromeda is vast and profound, filled with the mysteries of the universe. The enigmatic tales of Andromeda, beyond the reach of our eyes. What lies in the future of Andromeda? Revealing a different aspect of the cosmos? In the galaxy of Andromeda, where the spectacle of light and darkness continues. Today, in our 7th session of Introduction to Astronomy, we will explore the astonishing identity of the Andromeda Galaxy and contemplate the fate of galaxies. Subscriptions and likes greatly empower our video production. The Andromeda Galaxy is the closest giant spiral galaxy to our Milky Way, situated approximately 2.5 million light-years away from Earth. With a diameter of about 220,000 light-years, it is roughly twice the size of our Milky Way. Andromeda Galaxy boasts around 1 trillion stars, with some being much brighter and younger than those in our own Milky Way. At its center lies a supermassive black hole, surrounded by a bulging region filled with stars, dust, and gas, as well as a flat, rotating disk. The spiral arms extending from the disk showcase the galaxy's history of star formation. Andromeda Galaxy is accompanied by several satellite galaxies, among which the largest ones include M32, M110, and M33, exhibiting elliptical or spiral shapes. Formed through the merger of various primitive galaxies approximately 10 billion years ago, Andromeda Galaxy stands as one of the oldest galaxies formed after the Big Bang. In about 4.5 billion years, it is anticipated to collide with our Milky Way, giving rise to a new, massive galaxy. Information about the planets existing in the Andromeda Galaxy is still not well known. With approximately 1 trillion stars in the Andromeda Galaxy, it is presumed that some of them may have planetary systems. However, observing planets in the Andromeda Galaxy is extremely challenging. This difficulty arises from the fact that Andromeda is located about 2.5 million light-years away from Earth, making the planets appear very faint or even invisible. Research on giant planets within the Andromeda Galaxy is still in its early stages. In 2009, a candidate planet was discovered orbiting a star in the Andromeda Galaxy. This candidate planet, considered the first one found in the Andromeda Galaxy, is estimated to be a giant planet with about 6.4 times the mass of Jupiter. It appears to orbit a star known as M31 in 2008 12A in the Andromeda Galaxy, which is considered a new type of recurrent nova that explodes annually. As our understanding of the Andromeda Galaxy's planetary systems is limited, ongoing research and advancements in technology may provide more insights into the presence and characteristics of planets within this distant galaxy. In 2013, 2 additional candidate planets were discovered orbiting another star in the Andromeda Galaxy. These planetary candidates represent the second and third such findings in the Andromeda Galaxy, estimated to be Earth-sized planets with approximately 0.7 and 0.6 times the mass of Earth, respectively. These candidates appear to orbit the star M32001 in the Andromeda Galaxy, which is part of the satellite galaxy M32. It's important to note that these planetary candidates have not been definitively classified as planets. They were discovered using a method called microlensing, which utilizes the phenomenon of bending the light of a star when it aligns with a planet. While this method allows for the inference of a planet's presence, obtaining detailed information such as its size, mass, and orbit is challenging. Additionally, microlensing is a one-time event, making it nearly impossible to reobserve the candidate planets. To gather more information about planets in the Andromeda Galaxy, more powerful and precise observational instruments are needed. Space telescopes currently in development, such as the James Webb Space Telescope or the Louvre Space Telescope, could contribute to exploring the planets in the Andromeda Galaxy. I'll provide a detailed explanation of the collision between the Andromeda Galaxy and our Milky Way. The Andromeda Galaxy and the Milky Way are the two largest galaxies in the local group, gravitationally attracted to each other. Currently, the Andromeda Galaxy is approaching our Milky Way at a speed of approximately 120 km per second, and they are expected to collide in about 3.8 billion years. The collision between the Andromeda Galaxy and the Milky Way is anticipated to unfold through the following scenarios. Initial stages: as the two galaxies approach each other, their respective spiral arms begin to twist and stretch. The supermassive black holes at the centers of each galaxy start gravitationally attracting surrounding gas and stars, forming accretion disks. The accretion disks produce intense radiation, leading to the birth of new stars. First collision: when the two galaxies first collide, the stars in each galaxy scatter, and the gases mix, triggering a vigorous phase of star formation. During this phase, there is a 12% chance that our solar system might escape the gravitational influence of the Milky Way and a 3% chance of being incorporated into the gravitational field of the Andromeda Galaxy. However, due to the vast distances between stars, the likelihood of significant effects on our solar system is minimal. Intermediate stages: after the initial collision, the galaxies pass through each other, and their gravitational forces cause them to turn around for a second collision. The spiral arms of both galaxies transform into massive tidal tails and scatter into space. Additionally, the supermassive black holes at the centers of each galaxy approach each other, emitting strong gravitational waves. Second collision: when the galaxies collide for the second time, the stars mix, and the gases merge, initiating another phase of intense star formation. During this stage, there is a high likelihood that our solar system will be relocated to the outer halo of the new galaxy. The supermassive black holes at the centers also merge, emitting colossal gravitational waves. Final stage: upon complete merger, a new giant elliptical galaxy is born, known as Milkomeda. Milkomeda has a mass approximately 8 million times that of the Sun and is characterized by a low central density compared to existing elliptical galaxies. It possesses a massive halo composed of stars remaining from the spiral arms and tidal tails of the Milky Way and the Andromeda Galaxy. This collision and merger will result in the formation of a new, larger galaxy that incorporates elements from both the Milky Way and the Andromeda Galaxy. IC 1101 is the largest known galaxy in the universe, surpassing even the Andromeda Galaxy. It is about 50 times larger than our Milky Way, with over 100 trillion stars. Situated approximately 1 billion light-years away, IC 1101 is considered one of the oldest galaxies in the cosmos. IC 1101 has grown to its colossal size by absorbing other galaxies, mainly consisting of aging yellow or orange stars. At its core lies a supermassive black hole with a mass equivalent to 400 billion suns. Currently, IC 1101 is in a state of decline, no longer producing new stars. The process of a galaxy's demise entails the cessation of star formation, gradual extinction of existing stars, and the possible loss of raw materials like hydrogen gas due to interactions, mergers, or other disruptive events within the galaxy. It's crucial to distinguish the concept of a galaxy's demise from the Big Crunch. The Big Crunch is a hypothesis about the ultimate fate of the universe, suggesting that if the gravitational forces due to matter are stronger than the expansive energy, the universe might contract back to a single point. However, current observations indicate that the universe's density is much lower than the critical density, and its expansion is accelerating, making the likelihood of a Big Crunch very low in current cosmological theories. The death of a galaxy does not necessarily result in only black holes remaining. Instead, it signifies the cessation of new star formation, and existing stars gradually fade away through various processes. Smaller, cooler stars may become red dwarfs and persist for an extended period. Slightly larger stars might evolve into planetary nebulae or white dwarfs, cooling down over time. Stars significantly larger than the Sun could undergo supernova explosions, potentially forming black holes or neutron stars. Therefore, in the process of a galaxy's decline, the exclusive dominance of black holes is not guaranteed. Black holes represent just one outcome in the diverse life cycles of stars, and not all stars end their lives as black holes. Additionally, black holes themselves are not eternal. According to physicist Stephen Hawking's theory of Hawking radiation, they can gradually evaporate over billions of years.